Welcome back to The Explainer, everyone. Today, we're doing something a little different. We are shifting our entire perspective on chemistry. Instead of just viewing it as a massive, memorized collection of reactions, we're going to look at it as what it really is, a highly systematic toolkit. It's essentially the fundamental language that lets us break down the physical universe into predictable, incredibly measurable pieces.
So here's our roadmap for today's journey. We're going to kick things off with the language of measurement, then dive right into precision and certainty. After that, we'll explore the states of matter, figure out exactly how to categorize all this stuff, talk about chemical change, and finally, we'll wrap up with the grand, unbreakable laws of the universe. Let's get right into it.
Okay, so first up, to really understand matter, we absolutely have to have a universal mathematical language to measure it. Think about it. If scientists all around the globe are going to collaborate on decoding the universe, they can't be getting tripped up on conversions. They need to be speaking the exact same mathematical language.
And that gives us the 7 fundamental SI units, officially established back in 1960. You've got time in seconds, mass in kilograms, length in meters, temperature in Kelvin, electric current in amperes, light intensity in candelas, and of course the amount of substance in moles. Literally every physical measurement starts with these foundational blocks.
Now, from those 7 basic building blocks, we construct what are called derived units. It's basically a modular, interlocking system. If you divide distance by time, you get speed. Combine mass and volume, and boom, you've got density. It's like putting together chemical Lego bricks. But having a language is really only half the battle, right? Because in science, how exactly we measure something is just as important as what we measure.
To understand why this is such a big deal, imagine a real-world scenario. Let's say a teacher hands a mystery substance with a true weight of exactly 3.00 grams to 3 different students and asks them to measure it twice. What happens when unpredictable human error enters our perfect mathematical system?
Well, the results are actually fascinating because each student's error tells a completely different story about their methodology. Student A gets 2.95 and 2.93. Student B hits 3.01 and 2.99. And then there's student C, whose numbers are wildly different, 2.94 and 3.05.
This specific data perfectly highlights the difference between precision and accuracy. Think of it like throwing darts at a dartboard. Student A's measurements were clustered really tight together, so they were precise, but they completely missed that true 3.0 gram bullseye, so not accurate. Student B, they hit the bullseye tight and consistently, meaning they were both precise and accurate. And student C, well, they were just throwing darts all over the board, neither precise nor accurate.
So how do chemists actually communicate this certainty to each other? They use significant figures, or sig figs. Take a number like 0.0072. Those leading zeros, they're really just placeholders for the decimal, meaning you only have 2 significant digits there. But in a number like 70.40, that trailing zero is absolutely crucial. It proves the chemist's instrument was precise enough to measure exactly to that decimal point, giving it 4 significant figures.
And when we're crunching these numbers, we have to use strict rounding rules. We can't just accidentally create false precision out of thin air. The rules are pretty cut and dry. If the digit following the one you want to keep is less than 5, you just keep it as is, like rounding 1.752 down to 1.75. If it's greater than 5, you increase it, turning 1.756 into 1.76. And if it's exactly 5, well, you keep it if the preceding digit is even and increase it if it's odd. It's a clever little trick that ensures uniform communication across the entire scientific community.
All right, with our mathematical tools squared away, let's shift gears and look at the physical canvas itself. We're talking about matter, literally anything that has mass and takes up space.
As you know, matter exists primarily in 3 familiar states, and this is dictated entirely by energy. Solids have a definite shape and volume because their particles are just rigidly vibrating in place with minimal energy. Liquids, on the other hand, have a specific volume but take the shape of whatever container you pour them into. Their particles are flowing over one another with a bit more intermediate energy. And gases? They're the wild ones. No definite shape, no definite volume, they are highly compressible, and their particles are basically bouncing around randomly with maximum energy.
Now, the universe is obviously a pretty cluttered place, so chemists have to sort all this matter into a neat, organized hierarchy to make sense of it all.
It essentially boils down to 2 main buckets, pure substances and mixtures. Pure substances have an invariant, fixed composition. These are your elements, like pure hydrogen, which you literally can't split any further, and compounds, like baking soda, where elements combine in definite specific proportions. On the flip side, we've got mixtures, where things are combined but they still retain their own individual properties. These can be homogeneous, like salt dissolved completely evenly in water, or heterogeneous, like oil and water, where you can physically look at it and see the separate parts.
Of course, matter isn't just sitting there looking pretty. It's highly dynamic, it interacts, it combines, and it transforms. We track all of these transformations using something called stoichiometry. Take the formation of ammonia, for example. The universe dictates a very strict ratio here. Exactly 1 mole of nitrogen gas interacts with exactly 3 moles of hydrogen gas to form 2 moles of ammonia. There's no wiggle room. The math perfectly, beautifully mirrors the physical reality.
But we have to draw a hard line between a temporary shift and a true fundamental transformation. Melting ice is just a physical change, right? It looks different, but structurally it's still good old H2O. But burning a log of wood? That's a true chemical change. The molecular structure is fundamentally altered, and completely new substances, like ash and gas, are born out of the process.
And these chemical changes happen in quite a few different ways. Elements can join together in combination, they swap partners in displacement, they break down in decomposition, they burn rapidly in combustion, they can cancel each other out in neutralization, or they can link up into massive repeating chains through polymerization. It is an incredibly active microscopic world down there.
So what's governing all of this microscopic chaos? Well, all of these measurements and dynamic changes are bound by unbreakable historical laws of chemical combination.
Let's go back to 1750. This brings us to our first grand rule, proposed by Antoine Lavoisier, the law of conservation of mass. It boldly states that in an isolated system, mass is absolutely never created or destroyed during a chemical reaction. It only transforms. If you burn a piece of wood, the total mass of the resulting ash and the gases released will perfectly, exactly equal the original mass of the wood plus the oxygen it reacted with. The universe, it turns out, always balances its books.
Then, Joseph Proust comes along and drops the law of definite proportions. He realized that nature builds its compounds with incredible, unwavering consistency. A pure chemical compound will always, without fail, consist of the exact same elements combined in the exact same proportions by mass, no matter where on planet Earth you stumbled across it.
To really ground this concept, just think about water. Whether you pull a sample from a rushing river, a high mountain waterfall, or a deep underground well, the ratio of hydrogen to oxygen by mass will always be exactly 2:16, which simplifies perfectly to 1:8. River water and well water are mathematically perfectly identical.
And finally, John Dalton takes it one step further with the law of multiple proportions. He showed us the next level of complexity, realizing that an element can actually form more than one compound with another element. But here's the kicker. When they do, the masses of the elements that combine do so in small, distinct whole number ratios. It essentially proves that matter combines in very discrete, predictable chunks, not just random, messy smears.
Which leaves us with this one final, mind-bending thought to wrap up today. If every single piece of matter in the entire universe obeys these strict laws, if mass is always conserved and elements always combine in these precise, predictable multiple proportions by mass, what fundamental, invisible building block is hiding beneath it all, making these mathematical rules actually possible? Well, answering that exact question is what led scientists straight to the atomic theory. Thank you so much for joining me on this explainer today, and I really hope this gave you a powerful new toolkit for looking at the world around you. Catch you next time.